What is a matrix? A matrix is a two-dimensional vector, or a vector is a one-dimensional matrix, whichever way you want to look at it. It's a grid. Or you could think of it as a table if you're used to something like a spreadsheet program. So a vector might be 1, 2, 3. A matrix might be 1, 2, 3, 4, 5, 6. So it's just an additional dimension. Matrices are generally considered row major. That means when we say this is a 2 by 3 matrix, it's number of rows, number of columns, and often you'll see it be an m by n matrix. So m is often the row count, and n is often the column count. Of course, you can use whatever variables you want, that's just common. So a matrix is just a grid. Now, why 2 dimensions? Why not more? If you have more than 2 dimensions, it's called a tensor. So you could have a 3, 4, 5 dimensional, and it's just, if you have a tensor A, and we'll do squiggly, and let's say it's a 3 by 2 by 9 by 6 by 4 tensor, then you could have element A of, let's say, 2, 1, 8, 3, 1 would be one of the elements. There's an additional squiggle to tensors. Tensors are a more advanced mathematical concept used in fancy physics and other things. Tensors aren't just a clump of numbers. They are a clump of numbers with special properties. And what properties are there depends on what you're doing. So we're not going to get into tensors. We're only going to do the grid, the two-dimensional grid, that's a matrix. Quick side note, if you've ever used the Torch neural network library, or mathematics library in general, because it does more than neural networks, they use the term tensor to describe a matrix of any size. And that's just what they call it. It doesn't inherently have any special properties. They just expect you to handle that part. Some other mathematical libraries may use the same word. In programming, if you see the word tensor in a generic library, it probably means it's just any dimensional clump of numbers, and you are responsible for doing whatever you want with it. It's just a storage mechanism. It's a box. But for us, a matrix is a grid of numbers, a flat two-dimensional grid. So what do you do with matrices? First of all, you can do element-wise just the same. You could have 1, 2, 3, 4, 5, 6, and 6, 5, 4, 3, 2, 1, and you add them. Both matrices have to be exactly the same dimensions for the same reason as vectors. It wouldn't make any more sense to have an extra row here. What are you adding? You're adding it nothing. You're adding a null. So you just do 1 plus 6, 2 plus 5, 3 plus 4, and you get another matrix over here. You can do anything, add, subtract, multiply, divide, anything element-wise, just as long as you specify it. So that's the easy part. Now, let's say we have 1, 2, 3, 4, 5, 6. Let's do something called a transpose. That's the capital T. Remember I showed you can write vectors this way? You just flip it. You basically look at it, the diagonal this way, and flip it. So you get 1, 2, 3, 4, 5, 6. This is a 2 by 3 matrix. This is a 3 by 2 matrix. And if this is A, we'll just use the same bar. This is A transpose. Take that away. Then if you have A, I, and J, this is just which one it is. You know how in a vector we had A1, A2, A3, so this would be A11, this would be A12, this would be A21, A22, A23, and so forth. Row, then column. Aij goes to A, J, I. You just take the imaginary diagonal and you flip it. It's not really a math operation, it's a structural operation. That's all the transpose is. You don't do any operations, you literally just flip it. Now we don't have dot products and cross products and fancy stuff like that. We do have matrix multiplication though. Well, let's say we have matrix A times matrix B. This is nothing like the dot product or anything like that. Not the dot, not the cross. It's a special multiplication. So let's say we have A, B, C, D, E, F. This is a 2 by 3 matrix. It's an M by N matrix, let's say. And let's say we're multiplying it by G, H, I, J, K, L. This is a 3 by 2 matrix. Let's call this P and Q. So what's the result going to be? What kind of matrix is this? It's M by Q. M by Q. So it's going to be a 2 by 2 matrix. Now what is every spot in here? It's a 2 by 2, so we have 2 spots. Well, this one right here is row 1, column 1. This is row 2, column 2. So let's say we have 1, 1, 1, 2, 2, 1, 2, 2. So this is row 1, this is row 2, this is column 1, this is column 2. So what is this? Right here, let's say we take, so it's 1, 1. So let's say we take the first row of this matrix. Notice that when I said it's m by q, that's the number of rows. So let's take a row. Let's take the first row, and we'll call that r as a vector. And we took the number of columns here, so let's say column 1 as a vector, let's call that s. This is r dot s, the dot product, r dot s. Let's take this column, we'll call this t. So over here, it's row 1 is r, column 2 is t, so this is r dot t. And remember what the dot product is, r dot s? It's a times g plus b times h plus c times I, just the dot product. So if this row is u as a vector, then over here, row 2 is u, column 1 is r dot r. Row 2, column 2 of the result, well, row 2 is u, and column 2 is t. That's how you multiply matrices. And you may notice one more thing. Let's think about it. How many elements does this have? This has the row count of that times the column count of that. In order for this to make sense, we're doing dot products of the vectors. A dot product requires the two vectors to be the same length. You can't do a dot product of a 3 long vector and a 4 long vector because, once again, you have, let's say, 1 times 2, 3 times 4, 5 times 6, 7 times, we're out of numbers. So when we are doing a dot product of a row and a column vector, those vectors have to be the same length, which means, see, we take a row here and the vector length is the column count. We take a column here and the vector length is the row count. N must equal P. So the result is m by q, but in order to be able to multiply the matrices at all, n and p have to be the same. So there is a restriction. You can't just multiply any two matrices, just like you can't dot product any two vectors. And another thing, you can't flip it. You know in algebra, if you have a times b equals 3, then b times a also equals 3. Not with matrices. And it should be unsurprising. We have this fancy, crazy definition of what matrix multiplication is. It's not surprising we can't just flip it. I mean, it's not, you can't just look at it and say, oh, well, of course you can't flip it. You'd have to do the math to prove it. Mathematicians are all about proof. But take my word for it, you can't just flip it. Matrix multiplication, vector multiplication, and normal number scalar multiplication are all different operations that mean different things. They're just called multiplication because it kind of feels like it. You know, I guess we could use a different word for it so it's less confusing, but matrix multiplication is not the same as other multiplication. So if you have a matrix A times a matrix B that is not necessarily equal to matrix B times a matrix A. Don't flip it. But what if? What if we had something else? What if we had A times B equals A? What is that? Well, going back to algebra, what if you have A times B equals A? Well, doing the algebra, we divide both sides by A, and we get B equals 1, because it's B times 1 and this is just 1. So this is what's called the identity matrix. It's not 1, but it's something that acts like 1 acts. In normal arithmetic, if you multiply by 1, nothing happens. It's the same thing here. If you multiply by an identity matrix, nothing happens. Once again, you can't flip it. Well, what is an identity matrix? Let's say we have matrix A is A, B, C, D, E, F. We want to multiply by something, and we want to get A, B, C, D, E, F. We want it to not change. Well, so we know that this is an M by N matrix, and we know that this is a P by Q matrix, and this is going to be an M by Q matrix. Well, M by N, we need to equal M by Q. N has to equal Q, because we want to get the same result back. So Q is actually N. Q is N. So that's the column count. So this has the same column count. But what about the row count? Well, remember, we take one row as a vector, and we dot it with a column. So the column length must be the same as the row length here to be able to dot the vectors. They have to be the same length. So P has to also equal N. This is a square matrix because it's a square. The sides are the same length. It's a square. So let me do something tricky. So this is 2 by 3. This will be 2 by 3. This will be 3 by 3. Let me put 1s diagonally and 0 everywhere else. What happens if we do that? Well, let's take row 1 here, and that's R. Row 2 here, that's S. Let's take column 1 and say that's T. Column T is U. Column 3 equals V. So row 1, column 1 of the result. We know we have 3 spots here. So row 1, column 1 is going to be R dot T. Row 1, column 2 is R dot U. And then we have R dot V. Row 1, column 3. Row 1 is R, column 3 is V. What is R dot T? A times 1 plus B times 0 plus c times 0. Well, we just have a, don't we? So that becomes a again. What about with the second column? A times 0 plus b times 1 plus c times 0. Well, that's just b. So that's b. How about the third one? Row 1, column 3. A times 0 plus b times 0 plus c times 1 is c. So that is your identity matrix. For any m by n matrix, the identity matrix is an n by n, 1's in the diagonal, 0 everywhere else. Because when you're taking the dot product, it's basically just selecting. It's almost like a mask. If you're painting or doing Photoshop or something, you have a mask, and the 1 is the mask. Or I guess the 0 is the mask, and 1 is where it's let through. So it's incredibly simple. M by n matrix, your identity matrix is n by n with 1's in the diagonals and 0 otherwise. And then you get a times I equals a. So it's a null operation. Now you may be aware in algebra, if you have a to the power of -1, that's 1 over a. And a to the -2 is 1 over a squared and so forth. They have once again reused notation because it's the idea of an inverse. This is the inverse of a, this is the inverse of a squared. So you can take the inverse of a matrix. You could have a, b, c, d, e, f. As a matrix, this could be matrix A, -1. They just put -1 up there where it's like an exponent. It's not exponentiation, they're just reusing notation again. But it's the same idea, because if you have A times matrix multiplication, its inverse, -1 equals the identity matrix. And algebraically, if you have A times 1 over A, which is the same as A times A to the -1, that equals 1. A divided by A equals 1, as long as A is not 0. And there's a similar thing for matrices. So this is why they've used the notation. It's a completely different thing, completely defined a different way. But it's the same idea. You can multiply them and you get the identity. So that's why. So this is how you can do algebra with matrices. Because, for example, let's say you had A times b, matrix multiplication equals c. And you want to say, well, what is a? Well, algebraically, a times b equals c, a equals c over b. You just divide b over. That's basically what you do here, because there's no division, but you could say a matrix multiplied b, matrix multiplied b inverse equals c, matrix multiplied b inverse. I told you you can't flip these around. You can't, put this one over here. You can't just reorder them. So you basically have to tack on to the end. But we know that this equals identity, and a times identity is a. So now we have a equals c times b inverse. So now we know what a is. You cannot invert every matrix. There's something called the determinant. You can invert a matrix if and only if the determinant is not 0. The determinant is complex enough, I'm going to do a video just on that. So right now, don't worry about that. So this is how you can do algebra with matrices. You can't move them around willy-nilly, but you can throw on inverted and non-inverted to move things over to the left and right of the equal sign. And of course, the matrices have to be multipliable in the first place. But if they are, there you go. If you think that matrix multiplication is a mess, it is. It's a mess like a child's room is a mess with toys all over the floor. It's not hard. Nothing I've gone over here is difficult. It's super fiddly. It's just numbers and numbers and numbers and numbers and numbers all over the doggone place. So once again, if you have access to a calculator, computer program, whatever, let it do it for you. You need to understand this, but it's stupid. Like, there's honestly no reason a human should be doing this. A human is prone to error. A human needs to understand this so they can do the math. But we invented computers to do all the stuff for us and not make mistakes, as long as the person programming the computer has not made a mistake. I recall in college that I had a calculus professor, and it was a novel thing. We took an exam, I think it was the midterm exam, and she had us bring in graphing calculators and use them. And I thought this was the most amazing thing, because up until then, you're a student. You take whatever the teacher says. You don't get to decide. But this teacher said, when you are in the real world doing actual work in an industry, whether it's a research industry, a building industry, engineering, as a professor, whatever, when you are actually doing real work for a boss and getting paid, you're going to be using a doggone calculator. It's true, you will be. You're not going to be sitting there with a piece of paper doing all this. They're not paying you by the hour or the year, either way, to sit there and do a bunch of math on paper. They want the job done. Move it, move it, move it. So you use a calculator. Plus, it's more accurate. So she said, the point of this class is to put down on a piece of paper for your potential employer to say, this guy passed my class, I certify, knows what he's doing. So she's testing us under conditions that we will find in the real world, which includes a calculator. So if your teacher doesn't do that, your teacher is wrong. I mean, once, like, they teach you this and have you do it by hand once or twice to make sure you understand it, yes. So the first time, like your first exam, you do it all by hand, but once you show you know how to do it by hand, you get the concept, now you use a calculator. So let's just hope you have a professor as good as the one I had. And just as a note, if you have a matrix that you cannot invert, you cannot find the invert of the matrix, it's called singular. One of a kind, I don't know. There's probably a reason for that, but they just call it singular. And those are the things you do with a matrix. You can do element-wise if the matrices are the same size. You can again do scalar too. If you have A, B, C, D matrix times E, a number, like 3, then that's just A times E, C times E, da-da-da. Just scalar automatically works in all the elements. You can do element-wise if it's the same size. And then you can transpose the matrix, which flips it along the diagonal. You can make an identity matrix, and you can make an inverted matrix, and that's how you do matrix algebra. And the last thing is the determinant. I mentioned the determinant in both this video and the vector video. The determinant is something else altogether. It's probably the hardest concept for both vectors and matrices, and there's not really a way to explain it. It's upper level math, and I'm going to do something called the Laplace expansion, or the Laplace, whatever it is, because on this channel we pick the easiest thing, easiest to remember, easiest to understand. But that one I'm just going to throw at you and say, this is it, just don't worry about it. I recommend going to college for math if you want to go further, or at least reading Wikipedia, and once you get halfway down that page, you're going to say, well, man, I better go to college for this. So while you start saving up your tuition, I'll be seeing you.